Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, we are going to continue something we've seen in a previous video where we actually tried to see what were the issues when we tried to integrate what is called an analytic function, or at least a function that is well defined on the path of integration, but not within the actual path of integration. And so that leads to issues as to how to evaluate that particular integral. And what we had seen was that there is a specific property in these particular cases that can be leveraged. So that's where we finished. And today what we are going to do is continue this calculation to give, let's say, illustrate an example of what is called the residue theorem. There are various versions that are more generalized than the one I'm going to provide here, but here this one provides the basically all the elementary steps that are required to then move forward to more generalized versions. Okay, so just a quick recap on where we were. What we want to evaluate is we've got a domain omega of the complex plane. Okay, so that's a complete domain. This domain has border d omega, so the domain is called omega, and then and it contains a point z0 that we're going to see in a minute. The border is d omega, and you want to know what is the value of the integral over the closed contour d omega of g of z dz. Okay. And what we had seen is that because g, the function g, in the case we're looking at, is actually a well-defined and behaved function f of z, and then divided by z minus z0, then there is a singularity occurring basically at z0, and it turns out that it prevents us from making, let's say, a very quasi-trivial calculation that would set the whole thing to zero. So we can't do that, we can't use that, and so we need to do something else. Now, the property I've mentioned usually gives zero to an integral over a closed contour, but although it's not applicable exactly in that case, it's still applicable to a case that is a bit similar to it, where we kind of patch together some pieces of curves in the complex plane. And this leads to a result we obtain that essentially the value of that integral is actually independent of the closed contour you draw around the singular point. And that's a property that we are going to use basically here. So what we are going to use is basically we choose d omega prime as being what I'm going to call C, and then of radius epsilon, and then centered as z0. So here, let's be clear on what these things mean. So this means that this is a circle. Then this is the radius of that circle. And this thing here is the center of the circle. So there are plenty of ways to write these things. Now, if you have, so basically what we are going to do is parameterize a circle with a single variable. The radius of the circle here is going to be fixed. And in fact, I'm going to make this circle radius tend to 0, because again, it's actually independent of the contour, the shape, the size of the contour, as long as it's enclosing z0. So the goal is to take a circle that is basically infinitely tiny. So I need to write specifically what is this particular parameterization. So I'm going to say that z is equal to, z is equal to, z is going to be equal to z naught plus epsilon exponential I theta, where so z0 is a center, and then epsilon exponential I theta is basically how you define a circle in the complex plane. Now you can view that by decomposing this part, if you will, as being, in case you're not comfortable, that's basically epsilon cosine theta plus I epsilon sine theta. And then if you remember that in the complex plane we represent things like x and y, then you're going to draw a circle basically with the angle theta of that circle. So that's what we are going to do here. So what we are going to do, let me then depict this circle here. We basically have a tiny, let me remove the z0, yeah, but basically we've got a tiny little circle with a radius epsilon that tends to 0 around the pole. Okay, so what that means is that if z is equal to that, z0 is constant, epsilon is constant, the only variable is theta. So when I apply that to dz, I get d of z0 is 0 because it's a constant, epsilon is constant, so the only thing that is going to be differentiated is exponential I theta with respect to theta, because that's the only variable here. And so I'm going to have I epsilon exponential I theta, and then d theta. So that's what I'm going to get here. Now what I can do therefore is basically write that the integral over any path d omega g of z, in fact let me write the function with the pole visible, so f of z, z minus z0, dz is going to be the integral. So I can write here, just for the sake of it, over the circle of epsilon z0, the same function, f of z, z minus z0, and then dz, and that's still closed. And then I can replace now with this single. So I parameterize my circle with a single parameter theta, and therefore this kind of complicated looking things where I simply describe the domain of integration and I say that this domain is closed. Now I'm going to simply write the values of the parameter that I'm allowing. So here, replace by theta equals 0 to theta equals 2 pi. Okay, so that's my domain of integration for the variable theta. Then here, so far I'm writing simply f of z0 plus epsilon exponential I theta. Here, z minus z0 is actually epsilon exponential I theta. And dz, we already said, was I epsilon exponential I theta, and then d theta. So what we see is that essentially we get that the epsilon and the exponential I theta basically cancel out at the numerator and denominator. So we are going to get that this is the integral from 0 to 2 pi. And then we have I f of z0 plus epsilon exponential I theta, and then d theta. And now what I do, that's the last thing to be done, is basically I say, yes, okay, but I need to take the limit when epsilon tends to 0. So this is equal to, when epsilon tends to 0, the integral from 0 to 2 pi, I f of z0, and then d theta. So we see here that we've got I times f of z0. This is constant, right? Because the only thing I'm integrating over now is theta. So what I end up with here is basically I times f of z0, and then integral from 0 to 2 pi, and then d theta. And that's 2 pi I, and then f of z0. Okay, and basically that's it. You're done once you have written that. So we can essentially work this out in the following fashion. we say that the integral over any kind of d omega of some function f of z over z minus z0 dz is equal to 2 pi I f of z0. Okay, so sometimes the way this is presented is basically you define so let's put here that f of z0 is equal to the integral over the circle epsilon z0. So you could write that this is sorry, I need to do something else here. So you can say that this is 1 over 2 pi I, the integral over the circle epsilon z0, and then of f of z, z minus z0, dz. Okay, and then you simply interpret this as, you call that the residue. So you call that the residue that's actually the residue of g at z0. And so essentially sometimes the way this is actually written, I'm going to erase very quickly here. So you simply say that you've got a function with a pole, so a singularity, which is as 1 over z to here 1 over z, and basically you would get so like first order kind of degree singularity, and then you simply say that this is equal to 2 pi I times the residue of g at z0. Okay, and basically that's how this is going to be defined. But sometimes it's just presented in that fashion. If you've got this particular expression, then that's how you're going to evaluate it. Okay, so it kind of doesn't matter the way you want to represent it. The bottom line is that you end up with the actual result. So that's called the residue theorem, no matter which form you kind of look at it. Is due to Cauchy, so usually you may see that as Cauchy's formula or Cauchy's residue theorem, and basically it helps very much finding out plenty of interesting integrals that otherwise are quite complicated and intricate to evaluate. So that's it. If you've got any questions or comments, please let me know in the description, in the comment section, and otherwise see you in the next video.